I'm Prajwal Anand, part of data science team at Analytics Vidhya. For those who have joined us for the first time, let me give you a brief introduction to the DataHour sessions. The DataHour is a series of webinars conducted by Analytics Vidhya and led by top industry experts. It is the fun way to understand concepts of data science and from the leading players of data tech domain. And as the name suggests, it's 1 hour dedicated to data. We are hopeful that these sessions are going to be a great source of enrichment and value added to our community members. Now, on to our session today, which is how to tackle overfitting. Overfitting is a serious issue in machine learning world, where a model fits very well in the training data, but the performance deteriorates in the test data. The session will cater around different methods to tackle overfitting. In this data hour, the speaker will cover how to reduce overfitting from the data preparation stage and what are the different things to look after while selecting cohorts. Then what are the different tips and tricks that can be followed to tackle overfitting in the model building stage, like use of regularization, covariate shift analysis, model ensembling, etc. I hope you are excited to attend this data hour with us. Before we kick things off, I hand it over to our speaker. A quick recap of our housekeeping items.
So we are recording the session, and the recording will be available on YouTube channel.
Please use the Q&A section for asking any questions you might have during the session, and we will do our best to answer them as the data progresses towards the end. Lastly, we will share a feedback poll towards the end. You are all requested to kindly fill that up before leaving the session. Now, on to our speaker in this session of DataHour, we have Subodip Mukherjee with us. Subodip is a data science professional with 7+ work year experience, currently working in Amazon as a data scientist part. Prior to Amazon, he has worked in Citi, ITC Infotech, and Rainman Consulting. He has cross-domain experience and experience in FMCG, retail, HR, reliability spaces, and academic-wise, he has done masters in statistics from Calcutta University in Kolkata.
All those who have not filled the poll, please fill it.
Hello, sir. Hello, everyone. Can you guys hear me? Please let me know in the chat section. Okay. Prajwal, can you please enable my screen sharing option?
I have made you the co-host, so you can share them.
Okay. Yeah, I can. Hello, everyone. So welcome to the session. And today we are going to dig deep on how to tackle overfitting, right? So So, okay, there are some Bengali comments as well. That's fine. But I want like if you can comment in English so that other can also get to know. Okay. So yeah. So today, so as Prajwal mentioned that overfitting is, yeah, we can, Abhinandan, we can connect later. I think you guys can follow in my LinkedIn to get about more of your personal things. Okay. So that is fine. But I think we can focus because since we have only 1 hour, right? We can focus on the topic. Yeah. So this is, so overfitting is a very serious issue. Like a lot of the modelers or data scientists who fit different predictive models in their career, right? When they fit the model on a data very well, but over a course of time when they test out their model, right, they see that the model is not holding. What it leads to is reduction in sales of the company. It directly may impact the profit and loss of the company, and the entire strategy sometimes also gets screwed. Okay. So, and this is not maybe due to, sometimes this is not maybe due to the bad quality of the data. A lot of data scientists usually call them as the data is not good. The data is not of a good quality, but that is not the case always. So if you take some proper measures while creating the model, right, you can actually reduce the overfitting by a huge margin. Okay. And today in the next 1 hour, we are going to go over that, and we will see that different techniques. And even from before a modeling standpoint, means before you start off with your predictive model, you will know the techniques that how to prevent overfitting at that stage as well. Okay. Yes, Abhinandan, it is mostly bias variance problem, but we will go into more details, okay, into that. So yeah, so before we go, so this is for the layman people as well who don't know, who does not have any exposure to predictive models. So for them, this slide is dedicated to them, and also to the others that because these terms I will be going to use a lot in the presentation going forward. So please, so for that, I just want to know that what these terms I mean when I will be using this. So the first one is called predictive model. Okay, so the first one is the predictive model. The predictive model is nothing but it is here you try to find out the relationship between a factor that can be a sales of next year, or it can be whether the customer is going to default on a loan, right? Based on their previous activity, right? And after you build a relationship, you will try to predict that, okay, out of my customers, who is going to present customers and based on their present attributes, right? Who is going to default on a loan? Okay. Or given my present this year's sales, what will be the next year's sales? Okay. You want to predict, and your business will build strategy based on that. Okay. This person is going to do a default in your loan. So I think we can do more checks on him, right? Before giving him the loan. Or if my sales is going to be this, okay, so then where are my weak spots? Which are my strong spots, right? So these are the different things that you can get from a predictive model. So it will first establish a relationship between what you know and a variable of interest which you want to know in future. Okay, so it is just like a thing. So I don't know how many of you are conversant with astrology. I don't know. A lot of people don't believe it as well. So what astrologer, when you go to an astrologer, what he does is first he will look at your hand or maybe an horoscope, and he will try to find out that using that data, he will try to find out what is going to happen to you in future, right? So using your hands data or your date of birth, so that will be his input, and he will try to output that what will happen to you in future. The same thing, it can happen in business, but here we will more rely on the science part, right? And so there is no taboo in it, and we will try to establish this relationship mathematically. So that is first, which is a predictive model. The second important thing that is that the terminology we will use is dependent variable. So the dependent variable, this is actually the variable of interest. So in case of suppose sales, right? So the sales for next year. So this can be the sales of next year, the variable that you want to predict in your future. So this is an event that you want to predict in your future. So that is can be sales, or whether a person is defaulting in your loans. So that can, so these can be your dependent variable. So this is the most important variable which you will use to predict. The next part is independent variable. So these are your known factors. Maybe I know your gender, I know your age, okay, I know your previous transaction behavior, and based on that, I will use this variable to establish my relationship to get your future sales predicted. Or I will use your how many credit cards you have currently, okay, or how many times you have defaulted in the past, right? I will use those important variables to predict that whether you are going to be defaulting in your loan in future or not. So that is called independent variable. Okay. The next important thing is observation window. Okay. So what is observation window? So this is very important. This is the time frame at which you will be observing your independent variables. Okay. So sometimes it depends on your business, and I will come to it more in details in the later few later slides. That it can be first, it can be sometimes 2 years. It can be last 2 minutes as well. Okay, so suppose suppose in my current role, where we try to predict that when a machine is going to break down. Okay, so over there, like 1 week to last 3 days data, that also becomes important. So that if I am running my machine more in the last 3 days, right? So my there is a higher chance of breaking down vis-a-vis where for the machines where I'm not running it very high in the last 3 days. So it depends. So that is the period that we use to define the independent variables, like your customer behavior, like your previous sales. Like I can take last 1 month, last 2 months, last 1 year, last 2 years. So this will be my observation window. In this time frame, again, I'm saying in this time frame, we will try to observe that our independent variables. The next one is a performance window. So this is the time frame when we want to see that when we want to measure our dependent variables. So sales in next 1 year. So in that case, if I'm in today, right, I will take the next 1 year's data as my sales. So maybe in last year of September, if I build my model based on that cohort, right, I will take data till this year. So that is my next 1 year data to predict the sales. Or sometimes due to so banks usually then predict the faults or defaults, right, or in your loan or a credit card. What they used to do, maybe let's say sometimes they have a 90 days days per due window. So it is called 90 DPD windows. Okay, so greater than 90 days, if he is defaulting continuously for 3 months, then we will call him a defaulter. So, and our model will also try to predict in the next 3 months how many people is going to default. So that is called performance window, the time window that we take to define my dependent variable. The next important thing is train data. Okay, so after you build your, so this is the data on which you will build your model on the data. Okay, so this is the exact data on which you will build your model. And there is one data which is a test data, which can be from inside your train data, a part of a train data. So suppose you have a data of 100 rows, you can use 80 rows of them for your training, and 20 rows of them can be for your testing. And that can be also from some another time frame as well. Another 100 rows coming from some another time frame that you can use as well as your test data. Okay, so these are mostly the different terms that we will going to use. We will deep onto test data in the next few slides. Okay, so please let me know, guys, in the comment section that if you have any questions. Okay. Okay, observation window and performance window, right? Validation data, I am coming now, right? Yes, independent and okay, independent variable, observation, performance window, and observation window, I guess, right? These are the different things that is coming. Okay, yes, I'm coming to this. Okay, yes. So observation window, first of all, it is the window. So it's for a modeling window, right? So again, if I go to your past astrologer thing, right? So astrologer needs some data from your past to validate it in future, right? So observation window is the time frame where you actually create. I will come to these questions of L1, L2 and all, right? So at the end of the session, you will get all the clarity. Okay, no worries on that. Okay, so for observation window, it is actually the time frame to depend your independent variable. So suppose you have to build a model where you want to predict the sales of next year based on previous year sales. Okay, so you can use previous year sales as an input to a machine and it will throw out an output. Think of a coffee machine. Okay, so a coffee machine, always what it gives, it will take the input of a coffee beans and give you latte or a cappuccino, right? So it is the model, predictive models are like that. So it will take the input of some inputs and it will give some outputs. And there's an input should be relevant, first of all. Okay. So the independent variable, so the independent variables are those input variables that you put to get the next year's sales. So it can be last previous year's sales that you can put in and it will put out the next year's sales. That is one. Independent observation window is actually the window in which you will define your input variables. So you will obviously take a time, right? So you can take like last 1 month sales, you can take last 2 months sales, you can take last 3 months sales and all. Is it dependent variable effect? And yes, independent variable is the cause, dependent variable is the effect. So independent variable is the input. Dependent. So here you have given it reverse. So dependent is the output. Yeah, and independent, I think you have given both as dependent, but independent is the input. And you will establish a causality relationship and then you will just predict. So the observation window, it will be the time frame when you define your independent variables. So how much sales I should take to predict next 1 year sales. It can be 1 month, it can be 1 year, it can be 2 years, it can be 3 years. So this time frame is your independent, is your observation window. Performance window is how much you want to predict. So what will be a time frame of your dependent variable? So it can be 3 months and it comes from business usually. So it can be 3 months from now, it can be 4 months from now, it can be 1 year from now. So that is your performance window. Okay. And the other thing is, I guess, trend data and test data. So suppose that is the entire topic that we are going to discuss. So suppose you build a relationship on your whole data set. Okay. You define your relationship on your whole data set. Okay. So now, what will happen that you are thinking that, okay, I have built a very good relationship and I am predicting very well. Okay. Yes, observation window is the past time frame. Yes, and the performance window is the future time frame. Okay, from in which you want to predict. So trend rate. So yes. So now you can build like on a data set fully. You can take all of our data set that you have and build a model. Can you guarantee me that tomorrow, if a new data comes in, your model will hold? Your model will give as good as performance with respect to what you are getting in the past? No, right? So therefore, that you need another data set which you will use to validate the performance of your data. Obviously, trained data, it will never overfit. From the test data, it will try to overfit. And I will come to the later in terms of the data or variables, okay, which are the different cases. Got it? Yes. I guess I have answered the questions. So I can move to the next part, right? Yeah. Okay. So before going into the what is overfitting, right? We need to analyze what is a bias and what is the variance component. I think someone has some questions on what is bias and what is variance. Okay. So what is bias, right? So suppose you have built a model. Okay. So this is like your, yeah. So suppose this is like your actual data. Okay. So these dots are your actual data. It can. So this is so these are the case of your actual data, right? And here you have built a relationship which looks like this. So here you can see that this difference, right, between your actual and the built relationship that you have built using the independent variables, there's a gap between this. Okay. So this gap is called, bias. On the contrary, here you see that in this model, right, here this line is actually estimating all the points, right? So here we can say the bias is very extremely low, okay, because it is estimating all the points, it is touching all the points, right? This is called MAPE actually. Mean square error is also something, but it is not exact thing. It is actually a square of this gaps, but MAPE is something which is more important. You can get it as a percentage and all. So the bias is nothing but it is the difference between your actual and your predicted model, right? Yes, the second graph is overfitting. I will come to that. Okay. So here, so in the first case, it is a lower bias, it's a high bias model, right? And the second case, it is a low bias model where the actual is where the prediction is actually touching all the points. Means actually you have got a 100% accurate model. Okay. And it's a more ideal case. But one thing is evident that idealism never exists. Okay. So if you see here, like this is ideal, it also brings a suspicion to your mind that, okay, if this holds in this data, will it hold in any other data set, right? This relationship is not looking too good. Too good things are always not very important, are not actual, real, right? You will see two good things are never real, okay? So you can't take this too good thing over here. So this is just like a too good thing, right? So now it will see that, okay, here you see if the relationship looks like this, right? It is look like this. But here, using this model is also giving you this value. The lines is not correctly predicting all these points very correctly. Okay, over here. So this is like in any other data, when you just want to present your model, the amount of deviation it has, right? So that is called variance. Okay. So variance refers to the changes in the model when using different portions of the training set, even different data set, right? So when you, yes, so exactly. So if the model actually states it, right, means if the model is if the model overlearns, right? If the model overlearns, it will happen that on a newer knowledge, when you will put it on a newer data set or new knowledge comes in, it will know nothing. It is just like memorizing your, when you have given your exams, right? It is just like memorizing your things too much, which in Hindi, it is called ratta marna, right? So if you are focusing on one thing and just learning it, if I ask you another question, you just know, I don't know what is this. So that is the thing. If I ask you those questions, right, that what you have learned by heart, right, where you have done that ratta, right? But when I give you that exam change, when in the exam, I just give you some different set of questions, you just fail. So that is variance, and that is called overfitting. So when you are in your own domain, you are fine. When you are just playing very good. Like it happens sometimes with India, right? India works when they play on Indian soil, they are like super. And when they just move to a foreign country, everything goes away. The scores goes down, right? So that is the thing. So if you practice more in your own soil, right, you will have a habit and you might play very well, right? So that is the thing. Okay. So, but when I'm giving you a new situation, you are not being able to cope it up. So your model should be like that. It might not be perfect, but it should cope any situation. That is the ideal case of a model. Okay. I will come to the next part. Okay. So this is the very important diagram that we have. Okay. So this is the case where you have, so if it's a bullseye, right? So in the bullseye, like here, all your dots are in one region. So it is low bias and low variance. This is ideal. And this is something you need in your model. Okay. This is a model requirement. So this is ideal. You need this, right? What are the other cases that may happen, right? So here it is high bias, right? And low variance. Okay. So here here all the dots are in same place, but the bias is high, right? So this happens for a case like simple linear regression. Okay. Okay. Here, this is actually called underfitting. So this is called underfitting, where in any data you will get same performance, but the performance is low. It is with some of the students, right? Every year they get around 40 to 50 marks, right? But every year they get it, right? That around 40, but 40 to 50 is lower in terms of 100, if the 100 is the full marks. So this is under, right? This is under performance. So this is underfitting. Okay. And okay, the next case is where it is low bias and high variance. Here, everything is near the bullseye, right? But low bias and high variance, but all the dots are actually spread across. All the dots are spread across. So this is a case of overfitting. Okay, this is the case of overfitting. So this is just like the India team who is playing very well in Indian conditions, and when they're going to any other Australia or some player, they are just screwed. So this is something that we are trying to do. Like in your own data, it is fitting very well. You are getting 99% accuracy. In the other data, right? When you just want to put the model, you are getting 20%. So that we are trying to reduce, because that is not, if a model shows this, then that model is not a model at all. Okay, if it does not hold over time. And this is where actually nothing is going good. So this is actually, I will use the term crap. This is like, it's not a model at all. You will definitely don't want this model. Okay. So this is something that you never want. This means that you are a not good modeler. Okay. That you should not get this. Okay. So these are the 4 things that so this is ideal. This is this state you want to attain. This state you want to reduce. Okay. Underfitting reduction, I think it will take another session, but there are a lot of models like XGBoost or machine learning models. So that is, yeah. So high bias, high variance. It means that your model is either not been able to predict anything, or as well as that your model is not holding in any other data set as well. So this is crap. This is nothing, no model at all. So this you don't need it. So if this is the case, then there is a serious problem either as a modeler in you or in your data. Right, you have to go to the business and talk to them that, okay, this is not possible. Means this modeling is not possible. But ideally, this case happens very less. I have 7 years of career. I haven't seen this. Either this happens, or this happens, or this happens. Yes. Okay. Okay, so next I will come to the how to control the overfitting, and this is the overfitting case, right? And we want to reduce this case. That you should get a good model, and your good model should hold everywhere, so that from here you can go to this state, which is the ideal state, which is the best state. Okay. So here the different phases of controlling overfitting. Okay. So what are the different stages? It is, the first one is cohort selection. So you can. So by judicious use of selecting your cohort, you will be able to reduce overfitting. And how, I will show it later. The next one is data and feature selection. So based on your data and using some judicious methods to select your feature, you will be able to reduce overfitting as well. These are pre-modeling techniques. You don't need any model over there. The next one is right model selection. Okay, that you have to select a right model, and in the modeling stages, how we will be able to reduce overfitting. So that will be the expert. So I will come to the next part, which is like cohort selection. Okay. So next part is the cohort selection. So cohort selection, there are 2-3 points that you need to know. Okay, at every step. So the first point which is that whenever you are selecting in your cohort, you should, if your business has seasonality inherent to it. Okay. This one, cohort selection, data and feature selection, and the third one is right model selection. Okay. So the first one is cohort selection. So for the cohort selection, suppose your business regularization is there, dude, no worries. I will cover. Okay. So cohort selection is something which you usually do while selecting your model, right? Which time frame, which performance and window and observation window you should choose. So suppose your business already has seasonality, because I worked in a fashion retail for a lot of days, okay, around 6 months. So I've seen that their summer preferences of customer is very different to your winter preferences of the customer. Okay. So suppose you build a model on your summer data, okay, or whole data as well, and want to use the same model on your winter data, it will not hold. Definitely, if there will be overfitting. Okay. So if you want to build a model on your summer data, your test data should also be summer, right? And it means your training data should also be summer. And if you want to build a model for winters, your training data should also be winter. Got it? So this is the way. The first thing is if you have to first gauge if your data has seasonality or not. So that is the risk. The risk will be that if you use one season's data for model building and use another season's data for your summer, right? So winter. So in that case, your model will not perform well. Another thing you can do, okay, I can take full year's data, but in that data as well, it might dilute both in summer, both in winter. So it might not overfit a lot, but underfitting will be definitely there. Okay, because you are not taking the preferences of summer and winter separately. So you should always take your preferences of summer and winter separately. So what not to do? So I'm coming. So build 1 year one model taking one season of data and deploy it for full year. That is not, you should not do. And build model on one season of data and validate on the other. Right. That is what the case I have told you. Build the model on summer, validate it on winter. Never. It will not hold. So what you should do, so first of all, build a model by appending one cohort for each season. So if you know that there is a seasonal impact. So if it's a half yearly, it can be quarterly. So take one cohort from each quarter. So take one data frame from each quarter, 1 month from each quarter. Build your observation and performance window according to it and combine them, just append them and then build your model. That can be one choice. The other choice can be build your one model for each season, right? So for each season, if you have 4 seasons, build separate 4 models and deploy it by running whenever. So you have a time frame attached to it. So if condition, right? So if this time frame is there, run this model, score with this model. If this time frame is there, if it's in October, run it with the winter one. If it's in July, run it with the summer one, that kind of thing. So you can do this thing. So this will, and while developing as well, build fold models in that case, or build a fun cohort of data by appending 4 cohorts for taking one from each season. That you can do. This will remove your overfitting by a huge margin. The second one, right? Second one is also like, it's a subset of the previous one like that. So if sometimes for Indian cases more like we want to build models for festivals, that in Diwali, Big Billion Day. Capturing data model will overfitting. I will come. Okay. So, so when suppose for Christmas, for Diwali, for Ramadan, right? Make sure that you have chosen the right cohort. Suppose you have built a model on whole year and we're using that same for Ramadan. How it will hold? How it will hold for Big Billion Days? How it will hold for the SCL period, Christmas period, right? It will not, because a lot of people who have not done any other thing, right? I mean, who have not done sales in the whole year, they might now come and do the sales for your festivals, right? So this will definitely create overfitting, right? So cohort is date and yes, recording. Yeah, cohort, it means exactly date and timestamp is which month you want to take for your model building. That is it. Okay, so that is your cohort, and date and timestamp is important. If it depends on 4 seasons, you should take the date of 4 seasons separately, 4 different seasons date. In any month you can do it. and that depends on your business case. Okay, and you can take any date. It may differ within the month as well. So if that is the case, you can then take pre-month, post-month, and something like that. So that date and timestamp is very important. Timestamp. Okay, the other one is like what we should do. Like, so for a Ramadan or Christmas or Diwali data, if you are using, build a model on previous year's data on the same time and validate on the data of the same time as well. So your test data should also come from the same time frame, not from any other, and deploy that model in that time frame. That, okay, in this month, I will run this model, and my original model, I will not run, right? So that you should do. Okay, one more thing is, don't go too far from the original time frame, and the cohort should be closer to the current time, right? So here we are taking, suppose, data of like last 20 years to predict next year's sales. Don't do it. Okay, don't do it. The other one is that always take, right? Don't go beyond 2 years. First of all, that's the thumb rule. And if you are taking like always do a YOY or month-on-month analysis. Okay. Not covering the same time frame. This is a valid model of whole model. No, so for that I'm saying that, okay, for Ramadan, or so take the Ramadan's data only, for last year's Ramadan's data, and build your model on that and deploy it on that. So last year's Ramadan, it means you can take how much sales has been done in Ramadan, after Ramadan, maybe 1 month, after in the Ramadan time period of 1 month, and take maybe their previous 3 months data, or last year's in last 1 year, how much data you got. So, but build it. Your cohort should be around Ramadan. Don't take any cohort out of Ramadan. Got it? Don't take any cohort out of Ramadan. Take last year's Ramadan data, and based on that, build your model and deploy it in that fashion. Don't take the full year data and deploy it in the Ramadan time frame as well. So build a separate model on this cohort. Okay. And the last point, what we have seen, that, okay, don't go too far from the original time frame, and the cohorts should be closer to the current time frame. Don't take 20 years data. Do a month-on-month YOY analysis, year-on-year analysis, that how much your features are changing. If the feature has changed a lot, right? Suppose I have taken pre-COVID data now to build something on post-COVID data, it will never hold. It might not hold in my cases, right? So like in city, we have seen that the sales have moved from offline to online. So we have seen a lot of companies. We have seen Amazon also had a huge chunk of sales in the COVID. So in the COVID, pre-COVID data, if I use in the post-COVID to predict something in the post-COVID scenario, it might not hold. So you have to be judicious to take don't go too far into your cohorts. Okay, I will now go to the next part, and this is a very important part. Okay, there will be very yes, geographically as well. Like if you want to do an analysis, geographical analysis. Okay, so there is a separate type of model building which is called panel data. Okay, panel data model building, which is, if you have time as well, you can incorporate that. Otherwise, geography, see which geographies are actually holding, right? Have similar kind of data. Do an analysis, then build models for each geography types. Okay, do this analysis first, and then build your model on that. Don't build one model for all the geographies and deploy it. It will be off for some of the geographies. So the next part is data and feature selection. I'm sorry, I've not been able to take a lot of questions. I will take the questions at the end of the session because it's only 1 hour and I have to cover a lot of the topics. Okay, so the first of all, data. So the next part is data and feature selection. Okay, the first thing is definitely how your test data should be. So first thing is in-time validation. In-time validation is actually you should take while building your model, right? It should be coming from your own data. So suppose you have taken the data of whatever training data you have taken for the whole year, maybe you have taken a data, and keep 80% of it as your train and 20% of it as your test. Now, if suppose you have a very small data set, okay, so then there is something which is called k-fold cross-validation, which we will cover in the next part. Do that. Okay, that will help you to get that whether your model will hold in another part of the same data or not. And always keep these two data sets, that is the data part or the sample where you will train and the sample where you will test, mutually exclusive. Don't take overlapping observations or overlapping numbers over there. Always keep both these frames separate and mutually exclusive, means one should not overlap. Then the other, okay, if you have, suppose you have a city or a cross section like what someone mentioned, right? If you have a cross section like city in your data, right, or a country, take a stratified sample so that from each sample in your train and your test data, same proportion of observations lie. Suppose in your data, in your train data, you have maybe Kolkata, Mumbai, and Delhi, and your test data, you have only Mumbai and Delhi. That is also not right. Reverse is also not right. In your train data, you have Mumbai and Delhi. In your test data, you don't have Kolkata, right? Maybe you have in your train data, you don't have Kolkata. In your test data, you have Kolkata. Okay, that is also not correct. Don't do it, because in that way your data will your model will not see the whole data set, or your model will not be able to validate the whole data set, right? So always try a stratified sampling. How you should do it, I have given a code snippet. So there is a variable called stratify var. So in this train test play, so this is a 70% sample I have given dedicated for training, 30% sample I have given dedicated for testing, and stratify var will help me to stratify the sampling. So always do stratification. Out of time validation, this is just like, you also have to go like one cohort or two cohorts back. You should also do get one separate cohort of data, like last 1 year of data. Maybe you can take this year, on this years of data, you have built your model, take last years of data to validate it as well, along with the train test validation, to see that whether your model is time tested or not. Okay. Now, if in ideal cases, two cohorts should be selected. One forward, means from the time. So suppose this year you are building your data, build it on January's data, test it on maybe May or June's data once, if the data does not have any seasonality, okay, and also test it on maybe 1 year back data. So always you should do both, so that you will get to know that, okay, whether your model will be holding going forward as well as going backward or not. Don't rely on one sample. Try to put two samples if you have that thing. Holdout samples. Holdout samples is nothing but where you have your training data, you can divide it into small parts, 1, 2, and 3. So here you can train. Here you can use your hyperparameters to just test it out. Okay. And here you can, so this is your holdout sample. Okay. This is called holdout sample. This you can take into consideration while building your model. And here you can test your model. Okay. So this here you will just fit your model, right? And unless you are satisfied with the holdout sample, you will not touch this test data unless, so when you are satisfied with the performance in the holdout sample, then only you should go into the test data. So that is another approach that you guys can do. This is called holdout sample approach. So this is a sample code what I have given here. We can do it twice to get the holdout sample. No, this is not a fold strategy. Fold strategy is something I'm coming in next 5 minutes. Okay. The next one is, this is very important. This is called character stability index, CSI. Okay, this is a very important metric which will help you to get that in case of a data, this will give you a threshold, okay? A metric that whether your variables are not consistent in your train and test data. Okay, so this will help you in that. So how to do this, like the steps to do the same is given below. I've given like for each one step, I have given one line. Okay, take one independent variable. So the variable you want to see that whether it is going to be overfitting your model or not. Okay, so take one. So you have to do it for all the variables in your data set, which you want to fit it in your model. So first take out the independent variable from your trained data. Take out maybe one. Divide the variable into 10 bins. Okay, that is deciles, means 10 deciles, 10 percentile cuts. So there is a Python qcut, there is a function which will help you to do that in the pandas library, which will help you to divide your variable into 10 parts. If the variable does not have 10 unique values, right, or it can't do it, you can divide in 4 or 5 parts as well. That is fine. Now, for that variable, take, and this is we are doing from the training data, training sample, okay? Now calculate for each decile, calculate the minimum and maximum of it, okay? So, and store it in a separate data set. The next steps will be use this minimum maximum thresholds on your test data and again create the deciles on those variables. So suppose the same variable, it can be like age in your trained data, you created these 10 deciles, know the cutoffs that, okay, these are my cutoffs, put the same cutoffs and create the same 10 deciles in your test data for the same variable age, okay? Now for them, calculate this metric. So for each now, since you have deciles, right, you can just get the how much percentage of observations are there in each decile, okay? So there's number percentage of observations in your training sample and percentage of observation in your testing sample. And if you create, and this formula will create the metric for CSI, okay? And you have to finally take the mean of it across all the deciles to finally get the CSI value, okay? Now, if this CSI value is less than 0.1, you don't have to do anything. If it is greater than 0.1 to 0.2, so if it is between 10% and 20%, then you can, what you can do that, okay, you might have to look at the variable some more and you can do it. And how I will show you. And if the CSI is greater than 20%, then this variable is bound to overfit. Okay, then this variable is bound to overfit. And now finally you have to repeat the steps for all the variables to get the CSI. How it will look like this. So suppose this is the variable, these are the deciles. Okay, here this is the training percentage. So in greater than 720, there are 12% observations. In test, it has 11% observations. And the CSI will look like this. Okay, so here it is like 0.1, within 0.1, within 10%. So it is fine. So so this variable will not overfit in our data. Has a very less chances of overfitting. What if CSI fails? So definitely you have to see with using other correlation or information values, right? That whether it's an important variable to your model or not, or from a business standpoint. If it is not, definitely drop the variable. Don't use the variable going forward. Okay, don't use the variable going forward. If the variable has some predictive power, right, and still you are seeing the CSI is not holding, right, then use your outlier treatments. I don't know whether you guys know about outlier treatments. It is like flooring, capping, converting the variables into categorical groups like bin, converting the numeric variable into categorical bins, or combine the bins, see which area, which bin actually the CSI is not holding, try to combine them or try to make it as a category and use it as a categorical variable. So in that way, you will not lose your model's efficacy by a huge margin. You will lose some, but not by a huge margin. But you can use the variable, but your stability will also hold. So you need to bin it or tweet it in a better way. Is this similar to MI index matrix method? I don't know what is MI index, might be. You can go through Google on this. Okay, the next one. This is also very important. Manual information. Yeah, might be. But no, I think manual information, I don't think so. It is with mutual information, I don't think so. I think CSI, it is a character stability index. Just follow this. This is for the stability of the data, not how much. I think mutual information can be due to that how much can be it's a proxy of correlation metric, like how much it can be helpful for prediction. But CSI is a metric which will help you for stability of the data. Got it? Okay, the next one is covariate shift analysis. This is also you guys have seen in the thing in the AV page. So in order to, and this is specifically useful for a machine learning model. Okay. So here the first step is take out two equal size samples from the trained data and test data. So suppose you have a data of maybe 1 million. Take out 50K from test. Maybe you can take out 50K from train. Okay, whatever sample you have, you might have a sample size of maybe 1 lakh of a test. That is fine. Random sampling. Okay. Now, in the second step, For the test, so for the train data, create a tag 1. For the test data, create a tag 0. Okay, and append the two data sets. Okay, the third step will be run a machine learning model, preferably a random forest model usually works well, right? With respect to this 10 tag, this will be your dependent variable in this case. Drop your original dependent variable. Okay, just this is for your overfitting, and all your independent variables put it as your independent variable for this model. Okay, same sample size should be there. 10 tagging should be there. For train it is 1, for test it is 0, and build the model around it. Now take the variable importance of the variables. See if some of the variable is relatively very high in terms of like 50% or 60%, right? It is contributing to the variable importance. Variable importance will tell you that what is the order of the variables into segregating these two values, right? So take the variable importance chart, sort it by higher importance to lower importance values. If a variable is standing out over there, that is causing overfitting. Reason is what you have done over here, like you have created for your train data and for your test data, two taggings. If a variable is actually being able to segregate this 1 and 0, right? So then this variable is actually different for your train data and your test data. Okay, got it? So this is actually the variable has creating a segregation between your train data and test data. The tag is actually defining that which one is your train and which one is your test. So it will just create the segregation between them. Okay, if that is happening, your model is actually overfitting. Okay, and you can now check that variable of the CSI of that variable. Now you have not have to run as well for all the variable methods, right? And you can check the CSI, do the treatment, your model is done. This is a very good method of creating the of segregating. You're controlling overfitting. The next one is model selection. Now I think a lot of people will get a bit calm, right? Because I will come to their favorite topic. Okay, regularization parameter. Okay, regularization parameter works for some classical regression models, right? For linear models, as well as for logistic regression models like linear regression and logistic regression models. So you have an extra parameter, and it also has an extra parameter for XGBoost. Okay, XGBoost, I don't know whether you have heard the name of this, a gradient boosting, extreme gradient boosting method. It also has the parameter. So what it is does, right? So this is an underfitting scenario. This is an overfitting scenario. It will, so what happens that if you put lots of variables in the models, Siddharth, I think I have it in as an appendix, but I think we need a different session for that. Okay, to explain XGBoost. If you want, you can talk to the AV guys. Okay, I can help you to understand the mathematics of XGBoost. Okay, a short I will explain. Try to explain here. Okay, so what if you push a lot of the variables which might not add a lot of value in the model, but if you still force fit it, right? What will happen that it will definitely, the model is like that, it will try to utilize the variable and try to get the variables, but whenever to try to get the relationship. But whenever you use that variable, right, in order to predict, because that variable does not have a lot of value in the model, right? So over there it will over predict. It will not be of any use. It will be like a junk that we're forcefully imposing into your model. Okay. So what? So how regularization works? Okay. So this is your regression estimate. This is your data. This is your dependent variable. These are your sets of your independent variable. You will put this. So on your regression estimates, you will put one condition. Okay. And here, so this is called cost function, and so when a linear regression fits, it will always try to minimize this whole value. Okay, it will try to minimize this whole value because this is a proxy of the error that you are doing. Okay, so it will try to minimize the whole value now, and this is a hyperparameter. Okay, that you can adjust. So based on this, it will try to squeeze the values of the variables which is not adding any value, any value. Okay, which is not adding any value, which is causing this bias, it will try to squeeze the value of the variables. Okay, of those. So suppose you have age, you have race, you have maybe sex, you have, so suppose the sex variable does not add any value, right? And it has maybe a beta. Okay, so it has a coefficient of regression. So what this will try to do, that if it does not have any value, right, it will try to make its value as 0. So for this one is called lasso regression, and this one is called ridge regression. Okay, you guys can definitely get it in sklearn. They have implemented it. Okay, so the difference between these two is, for lasso, the values of the weights can be 0, and for ridge, it will never be 0, but it will be very shortened. It will be close to 0, where the variable is not fitting. Now the important thing is XGBoost. Okay, so this XGBoost, the parameter, actually the parametric form looks like this. So this is your first cut. I mean, after the first iteration, it will always put your mean, or it's a random cut. So that is the thing. And these are your values that you are getting at each iteration with each decision tree. So over here also you have this parameter of lambda, which is like, which will like reduce. This is a regularization parameter. It works similar, and it will just penalize your leaf. Okay, the values that is there in every leaf, it will just try to penalize that leaf. A detailed calculation I can show you, but I think today it is very difficult, but it will definitely try to penalize the leaf. Okay, it will just cut off the leaf. It will prune the leaf. It will help you to prune the leaf. Okay, and in that way, that if the leaf is of not use for a decision tree for a step, it will not use that. Okay, when to use lasso, when to use ridge. So suppose you want that your parameter, that you don't want the variables, right, at all, right? You don't want your variables at all, which is causing overfitting. Then you should use lasso, because it will shrink your values to 0. And suppose you want all the variables to be there, whatever is the lower, because sometimes business have the interpretation. They want to deploy, suppose on digital media, they want to deploy a lot of money on digital media. Now they want to see what is the importance of each variable. You want all the variables, whether it is small, whether it is large, then you can use ridge. Okay. Okay. So also one thing, this also eliminates, definitely feature selection, right? So it will always remove the variables. It means just like you will get 0. It can be used as a feature selection method. Okay. Also, these two methods has an advantage, like if you know about multi-collinearity, right? That is like, if two variables have is highly collinear, means they have high amount of association, like 90%. If one increases, the other also increases by 90%. There is a chance. Both of these methods penalizes that, and you will get one variable and it will remove the other. So there is a high chance of that. So that will also help you guys to build your model more judiciously. Now, next one is, I think this is also in hot demand, right? This is like k-fold validation. Okay, so k-fold, if you suppose you don't have a very big data set, and you have a small data set, and you might not take a 80-20 validation data set over there, you have not been able to take it, or you might not want to take it. So what is there happens is something which is called k-fold cross validation. So over there, a data, so this will be their enter training data. Okay, enter training data, you don't need a test data set over in-time validation or test data set over here. So what it will do, K means that it will take out one sample of the data aside at each step. Okay, and take the remaining K-1 samples, right? And train your model on the remaining K-1 samples, and test it at every step, test it on the remaining sample. And now the choosing of the sample is also random. So first step, it will choose this K, second, it will be the next, some different K apart from the first one, and it will go on. Finally, the model performance will be based on a mean across all the folds. A mean across all the folds. So here, but the caveat of this model is the training time is extremely high for if your data set size is higher, because here every step the sampling process will work. So at first step, it will just take some k minus 1. Yeah. Jackknifing is not the jackknifing is like you will just delete one part here, delete one part here. From there, both sides you are just removing. That is called jackknifing. Okay. So here it is selection of any part and you are just keeping it aside and using it for your testing set. For your testing, you will use the whole data set. Jackknifing, you will just remove the data set from both ends to just get rid of the outlier from both ends. But that is not you are doing. This is called k-fold cross-validation. Yes, because cross-validating, every step you are cross-validating, right? So here you are just here you are creating the model, here you are cross-validating. No, epochs is the number of iterations in a neural network. Cross-validation is on your training data set. Suppose this one-fold validation, okay, this is nothing but it can be your 80-20 validation. This is on your data set happening. Epochs is on your neural networks. If you want, it is the number of iterations you are running your neural network. Your number of iterations, your forward and backward thing is happening. Okay, backward training is happening, right? So that is epoch. K-fold validation can occur for any models, right? Over here, just like every step, your okay, stratified cross validation means here when you just do the cross validation, you are selecting the samples, you are using a strata over there. Just like I've shown you, right? I've shown you guys, right, that how to create a stratified sample. So exactly this sample, when you create this sample, it will be stratified over there. It will be based on a strata, so that the event rate is also maintained. The data, you have all the dimensions, or you have all the cross sections in your data. So that is the stratified. Random forest, you can make it for anywhere. Random forest, one thing is there which is called OOB. Okay, OOB, out of back samples. Okay, what out of back samples does is it's a single kind of a cross validation. Means you can think about it. Epoch is the iteration for neural networks. How many forward propagation and backward propagation it will have. That is epoch. So in the cross validation, the data is first broken into k parts. Since you are just breaking the data into k equal parts, on k minus 1 parts, you will just train the model, and on the kth part, you will change it. And this k will also change for every iteration. Finally, you will see that suppose in the k minus this part, you are getting maybe 80% accuracy. Here, maybe it can be 70% accuracy. Here, it can be 75% accuracy. So like this, and you will finally take a mean of all the folds to get the final accuracy metric. It is not based on one sample. For normal train test validation, it is based on one sample. Here, you are taking k times. It can be 5-fold, it can be 10-fold. Okay. So based on that, you are taking a mean, and you are so this metric will be much robust in that case, but it takes a lot of time. Okay, early stopping criteria. This is also very important and is a very good trick that you can use. Okay, and this works for machine learning models mostly, where you are running like tree-based models, or a neural network where you are using epochs. Okay, K is a hyperparameter. 5 and 10 is the most thing. Okay. 5 and 10 is the most most used. There are other, but you have to see that where you are getting good performance. That's like a hyperparameter you can just use. After CV, which model can be taken to test with the holdout data? Out of models, the accuracy may, yes, accuracy. So that is the thing, right? So accuracy, here it takes the mean of the accuracy. Okay. If the accuracy varies, we usually take a threshold of 20%. In the accuracy varying. Okay, you can take a threshold of 20%. If within it, if it's within 20% on the holdout sample, it's fine. Okay, if it is more, then you can think about it. Why scoring is negative, like negative absolute error? So that is, I think I will answer the question later. Okay, that is just like you convert your loss function. What is repeated random train test? So you are just taking different samples at each step. Is it similar to grid search CV and random search CV? No, grid search CV, is it similar? So CV, it is CV. It is cross-validation. Grid search and random search is something on your hyperparameters that you do. Okay. CV is common to both, and CV is this. CV is your cross-validation strategy. Got it? The other thing, okay, any other questions like this? So CV is nothing, so grid search is done on top of this. Yes, last I think we will, okay, I think I will have one more slide and then we can take all of your questions, okay? Yeah, all of them can be done. There is a pipeline package. Please go through it. You will get them. Okay, fine. The second one is the early stopping criteria. Early stopping criteria helps you to predict, okay, that when to stop in terms of a machine learning model. Suppose you have a random forest. Okay, so suppose you have a random forest model. Okay, so for the random forest model, you are training it for 1,000 trees. At each step, you can notice that what is the performance in your trained data or your test data. So it just starts off like this. Okay, your trained data is 50% accurate, test data is 50% accurate. Trained data is 51% accurate, test data is 51% accurate. Okay, if it is 53% accurate, it is 53% accurate. Okay, so it will go on like this is the first iteration, this will be a second iteration, this will be a third iteration, it will go on, right? A point of time you will see it is maybe 80% accurate. Okay, it is now 75 9% accurate. Okay, now it will go on increasing. Okay, it will now 85% accurate, it is 70% accurate. So always while fitting your model, always train till this point. Means where till the point where your trained data, so always test error goes like this. So it will always start underfitting and it will start to try to reduce the error. And after a point of time, it will again increase. Whereas in a training error, right, it will always decrease. Okay, you always try to fit it, then to the point from where the test error actually starts to increase. Okay, so this is called early stopping criteria. So in a model, there is already an OOB technique that I also mentioned that also can be used. It can be done manually. Also, there is a hyperparameter where you can split out the steps. That okay, after 5 steps, if the model does not improve in the test data, I will stop the fitting of the model. That can also be done in the model. So in the scikit-learn object, you can do that. So that can also be done. Okay, so that's it. And I will come to the last part. So this is like model ensemble, right? So ensemble, it is like combining different models. Now think of it, you have different models, which is maybe overfitting, right? Now you combine the scores. So because some model may be overfitting for 10 observations, some models may be overfitting for other 20 observations, but you combine them, right? You will come to a composite score, right? So this is combining different models. So you have created different random forest, XGBoost, and maybe some other model, linear regression, and you can combine them. Okay, so that is ensembling from a single. So that is called ensemble. So in a single sample, right, a single model, using a single model, how can you create ensembles? So these are called bagging and boosting. So though bagging, we usually use random forest and we know random forest, but that is not the thing. Bagging can be done on any data set. Bagging means that you are taking different samples, right? Different samples and fitting same type of classifiers, maybe fitting same classifier for different samples of the data. And finally, you are taking a consolidated or an average of the scores that the model is generating. That you can do. Bagging, yeah, random forest actually is a special kind of a bagging. Actually, that is a wrong concept. Those are not same. Bagging, you can do any models. You can do it on a linear regression model as well. You take different samples. So that is also like a bootstrapping. We used to learn it like a bootstrapping. You can bootstrap your data, build on different samples, and finally combine it. Random forest is an example of a bagging. But there are other, there can be any bagging techniques that can be used. Bagging, it means that you are resampling your data and fitting a same classifier for all the models. That is called bagging. Okay. Boosting, I think here, again, you are creating weak learners at each step. And so each step is dependent on the previous step. And you can reduce the overfitting over here as well. you get to decision tree after row sampling. So that's the hyperparameter, right? So row sampling, it is 80%. So it means that 80% sample will be taken. If you have a column sample by tree, right? So over there you mentioned 0 point, then again 80% of the sample will be taken. It's a hyperparameter, right? So you can just change it based on your data, based on your requirement. That is also a hyperparameter that it can be done. But here we are not talking of boosting or XGBoost parameter in the bagging sense. Bagging is like here you will just create different samples of the same data, right? And fit the model, and finally take a consolidated of all the model predictions. That is it. Ensemble from multiple methods. Sampling, oversampling, and features. Yes. Bagging can be rows as well, column wise as well. That can also occur. You can design your own bagging. Okay, that is a sampling step. Ensemble from multiple methods. Okay, so for random forest, the classifier is decision tree. For bagging, you can take a decision tree as well as any classifier or regressor, any model, any technique you can use. Okay, that is the main difference. Okay, so the next one is voting. Okay. So here we are trying to learn what are the ensemble from multiple methods, right? So the first one is called voting. Voting, it means that you create different models, different type of models. It can be one linear regression, one logic, you can use one XGBoost, you can use one random forest, and finally you are combining their outputs. Okay, so for two ways you can do it. So first of all, if it's a classification model, means where you want to just classify your data into 1 or 0, that's like a fraud prediction. Okay, so for them, what you can do, like you can create the models, like suppose random forest is predicting 1, random XGBoost is predicting 1, and linear regression is predicting 0. 3 models you have created. So here you can take the majority of the votes. Okay, that is one. This is called hard voting. And there are some where you can just get the probability predictions, or for linear regression, you can get maybe sales numbers. So it can be 0.9, 0.2, 0.1. Okay, and you can now assign weights to it. Okay, so these 3 weights, some should be 1, and it should be fractional. Okay, and you can add the weights, and finally you can create a weighted combination which will give you soft voting. Finally, you can create a combine using a weighted combination, and that is called soft voting. Okay, the next one is blending and stacking. So these are mostly similar. Yes. So this is mostly similar, blending and stacking. Here, what you do, like, so suppose you have created one regression model, linear regression model, one, okay, maybe the reverse. Okay, maybe you can create one XGBoost, one random forest, 2 models you have created. Okay, now you use the predictions of these 2 models. Okay, you use the so this is maybe prediction 1, this may be prediction 2, right? You use the predictions of these 2 models, and you can use one more model where you can use all the variables along with these 2 predictions as variables. So on top of this, it's a 2-stage model. In the first stage, you create maybe an XGBoost and a random forest, and take out their predictions and use it in a logistic regression model. That you can also do. Okay, so that is called stacking and blending. In the difference between the 2 steps is like one does k-fold cross validation, and in the stacking, and the other does normal validation, right? And you always have to do it on a holdout sample, not on your training data. Always you have to do it on your holdout sample data. Okay, got it? I think that's it. So these are the techniques I think I could cover in 1 hour. Right? So now I will go to the questions, if you guys have. Which gets overfit, and then we can use relevant techniques to overcome overfitting. Ideally, real-life datasets are more. You can go there and such in UCI machine learning library, there are a lot of datasets. You can see which one is there. Lecturer, please tell me ways to figure out anomaly detection in supervised learning. I think that is not a scope of this, right? There are a lot of ways to detect. I think that will take a different. You can talk to me in LinkedIn. Okay, all of your other questions from this, you can talk to me in LinkedIn. Okay, so you can talk to me on LinkedIn. How to overcome? Okay, imbalanced data set. You can do it by stratified sampling over right. That is oversampling, undersampling, or by a good stratified sampling. You will be able to overcome and overfitting. Okay. Okay. I don't use a lot of. You can use scale divergence and all. Sometimes that can be also helpful. I don't use. I use these methods and that is self-sufficient. Kaggle take any competitions data set. I think every data set has some overfitting, and always try to reduce overfitting. Okay, got it. Okay, I think there are some Q&As over here. Okay, so if you want hands-on sessions, anyone, I think talk to AV guys. I can show you some codes I have given, and I don't know if this material is shared. You guys can contact me LinkedIn, right? I can help you over there as well. I have given the links in this PPT. So that's okay. Grid search CV. Okay. Cross validation is cross validation. Grid search is when you are doing any hyperparameter tuning. Okay. Right. Okay. So if you are doing any hyperparameter tuning, you can use different combination of hyperparameter and see where your cross validation metric is minimized or where the gap is actually less. Right. So that is called grid search CV, and grid search means you will create a grid. Right. You will create a grid of a combination of all possible combination of your parameters. Right. And then try out and finding out the CV at every step. Where can we find the presentation of figures? I think that is okay. Got it, Saurav? I think I have answered your question on grid search CV. Yes, yes. Best value of hyperparameter using the grid search CV, and that is using Kaggle a lot. Okay. I have done some Kaggle competitions, but that is not. Okay. Can you get the model out of CV? CV is 5, which CV5 means it is a combination of 5 models. You can think of 5 samples. Okay. So, and combination of 5 samples and just combining them. Okay. Combination of 5 samples. You will just feed the model on 5 samples and you will just combine the model. So it's a combination kind of a thing. Not on one sample you are doing it. Got it? So every step, every modeling step is done on 5 samples. The accuracy mean can be combined, how the model reference can be taken out. So see, it is only done to validate your model. It is not done to take out your model. If your model is showing a good k-fold CV values, definitely take out your, then that model is holding good. Those hyperparameters is holding good. Got it? So CV is a validation technique. It is not a modeling thing. You are not building different models out of model, building same model on different samples. How R square and adjusted R square work? Okay, that is not a part of this course, but I guess adjusted R square work when you have lot of data. Okay, suppose what happens, right? If you introduce more variables, right, R square will go up. So you penalize the R square. Right, in the adjusted R square, you penalize the feature by its degrees of freedom or the number of features you have in your model, and that will help you to build much robust. So that will help you that R square will not increase after a point of time, and that will be more robust. Otherwise, you may land up to 100%. Yes, yes, sure. Please contact me in LinkedIn, because anomaly detection is a separate topic. I can take a separate DataHour actually on anomaly detection. So I need to know what kind of anomaly you have, right? Whether it's a time series anomaly or anything else, right? Or it can be solved whether during a supervised learning or unsupervised learning and all those. I need all those. I think you will. I think that you guys can do it. The LinkedIn profile is there in the invitation, I guess, in the page where the invitation there. They have the LinkedIn profile. Yeah. So I think if so that is a separate R for anomaly detection. You need one R is not enough. Okay, guys, any more questions? Because I think it's mostly, and I have to cover a lot. I don't know how much you have understood. If you have any doubts, right, you can talk to me in one-on-one in my LinkedIn, right? And we can talk over there as well. Yeah, sure, I will. No worries.